For this problem, we're interested in figuring out what the effective spring constant is between this force applied at a location along this bar and the delta measured at the location where this external force is being applied. To get started with this problem, we might go ahead and draw an effective construct that thinks of these different portions of the long bar as springs. So we might have a K1 for this region as given by here, and a K2 for this region below where the force is being applied. And once again, we have a force and we have a displacement, and we're interested in the relationship between these two in terms of a effective spring constant. So let's go ahead and use these three pillars or the framework that's outlined by Crandall, Dahl, and Lardner for solving these types of problems. Let's look at equilibrium first. So there are multiple ways to approach this. We could do external equilibrium first, or we could do something that's more like method of nodes that you have in a truss. So at this location, all right, what we see is there's an external force being applied, F, and there is this displacement associated with this force being applied, right? We expect it to move downward. And there are also going to be forces acting on this node from the springy portion above and the springy portion below. So we can write an F1 above and we can write an F2 below. And I've drawn them in the vertical direction because even though this spring is going to be in tension and this spring is going to be in compression, they're both opposing, the forces that we see are both opposing the direction we're going. So if delta is going downward, then these reaction forces from these springs are going to be going upward. If delta were to go upward, then the reaction forces would be going downward. Now, we can extend this idea of equilibrium like we do in trusses to the members and think about, all right, if this force has, or if this spring has on the top has to be opposing the motion, so it's pulling up, right? That means that the spring is going to be in tension, similar to how we draw the nodes in a truss system. When the force is coming out, that means that the member, if it's positive and coming out of the node, then it's going to be having a tensile effect on the adjacent member or the member associated with that. So we see that same behavior here. And this idea that we have tension in this spring then also means that this wall, okay, up here would be applying the force upward. Now, the spring below is experiencing a slightly, well, it's experiencing the opposite effect, not tension, but compression. So as we have a displacement going downward, there is a force going into this node in the middle, and so we need to have forces going into the springs here to represent the compression that this spring is undergoing. Now, we can write that at this node we have an external force F minus F1 and minus F2 is equal to 0. And that's fine, right? That's the balance of forces at this node, just like you would do with method of nodes with trusses. And this relationship also might seem a little bit silly because if we had just done the external equilibrium on the entire system, we would have gotten the same thing. We would have gotten that there's a force being applied externally, and then this wall is opposing that force, so F1 going upward, and this wall is opposing that force too, and so we have minus F2. Now, we wouldn't be obligated to draw all these forces in these directions, but we're trying to keep as many of these forces positive, so the directions we've chosen do make sense. Now, moving to geometric compatibility, we're going to think about how this displacement is similar to the displacements that the springs are experiencing. So for example, we have a delta 1 that's the displacement going downward of this end of the top spring. And if we think about a delta 2, we have a spring or a displacement that the spring on the bottom is undergoing. And what do we know? All these springs are connected, or these two springs, not all maybe, but these two springs are connected at this node that is experiencing displacement delta. So it's reasonable, right, to think, oh, well, if this goes down delta, then the top spring at this location has to go down delta. And the spring over here also has to go down delta. So delta 1 is equal to delta 2 is equal to delta. We're saying that the extension of the top spring is equal to the compression of the bottom spring, displacement speaking, and is equal to delta, the overall deflection of this node. Okay, so that's what we that's what we write down for geometric compatibility. For the constitutive relationships, we go back to Hooke's law, and we can write Hooke's law in a couple of different ways now, right? In terms of stresses or in terms of forces. Let's write it out in terms of forces. So if we have a force 1 here, and we have a K1, I guess I didn't draw that. I can add that though. Hold on. Yeah, so we're saying that this is a K1 up here. Okay, and this is a K2 down here. If we have force and we have a displacement, then we can say, they're related by a spring constant, K1. Similarly, F2 is equal to K2 delta 2. And remember, we're defining this in such a way that this delta 1 is positive, so F1 is positive. This delta 2 is positive, so F2 is going to be positive as well. So even though one is in compression and one is in tension, these constitutive relationships do capture the fact that the forces and the deltas as they're drawn here are going to have positive relationships. Now, the delta 1 can be written in terms of Flee, and delta 2 can be written in terms of Flee as well. So you can go back and take a look in session 3 when we go through Hooke's law and how we can figure out the displacements in these bars might be related to each other. And if we rearrange things a little bit, or we just say, okay, look, hey, F1 equals K1 delta 1. You see there's an F1, there's a delta 1. I can define the K1, right? The K1 is going to be EA1 over L1, and the K2 is going to be EA2 over L2. So we've got constituent relationships, we've got geometric compatibility, a geometric compatibility relationship, and we've got a relationship for equilibrium. Let's go ahead and let's look at some algebra, just combining terms. So we have F minus K1 delta 1 minus K2 delta 2, right? So that's taking this and then substituting these two expressions for constituent relationships into the equilibrium equation. And we can then write that we have F equals quantity K1 plus K2 times delta. Well, how did we get this? Well, we're rearranging things, and we also know that delta 1 is equal to delta 2 is equal to delta from the geometric compatibility. And K1 plus K2 now are serving as an effective spring constant. What does an effective spring constant look like for this system? Well, K1 is equal to this, and K2 is equal to that. So we can write out that the K effective is equal to EA1 over L1 plus EA2 over L2. In this case, the elastic modulus, well, okay, yeah, it's the same material, and we're saying also that the cross-section doesn't change. So we can go one step further and say that EA times quantity 1 over L1 plus 1 over L2 will be the effective spring constant. Now, if we just go back to this equation right here, and we remember that springs in parallel have their spring coefficients, spring rates, or spring constants add to each other, we can write out what looks like two springs in parallel. And this is counterintuitive, and we talked about this at the beginning of session 4, in fact. But because the displacement of both the displacements of both springs, or the deformations of both springs are the same, and the forces are different. Okay, that's a clue. Those elements are clues that we have springs in parallel. As we said previously in session 3 and session 4, if you have the springs in series, so for example, if this constraint on the end was not there and we just had a force at the end and we had the displacement being measured at the end, then we would have a system where the forces are the same in both springs while the displacements are different and they add up to the overall displacement that you would be measuring at the end. Those springs in series, of course, will then have the inverse of their spring constant equal to 1 over the inverse of 1 plus 1 over inverse of 2, right? So you can go back and review the differences between springs in series and springs in parallel. But let's go ahead and attempt to solve this problem numerically now with the expression that we have here. So this is in our attempt to figure out that what the spring effective spring constant is. And we can probably go ahead and, just do this with Google first, as we've been doing. And what variables do we have? We have E, A, and L. Okay, or two different L's. All right. So let's see here. We have this equation here, and we have all the numbers here. So E is going to be, or actually maybe we need this one, E, A, and then this quantity here. That would be simpler to type out. So E is 74 gigapascals. And what's the area? So it says that the area is 1.1 centimeters squared. So we'll do 1.1 centimeters squared. And then we're going to multiply by 1 over, let's see, what is L1? L1's the top one, and it says here, I guess it doesn't really matter because, we do 1 over the top and 1 over the bottom, but a distance 9 centimeters from the top, so that's going to be 9 centimeters plus 1 over the 14 centimeters, like that, okay? And if we do this, whoa, we get some kind of wild new units here, right? That's not necessarily the most, how do you say it, liking to what we want. I don't think it's going to be able to give it to us. Can we do this in newtons per meter? I don't know if Google's that smart. Oh, it is that smart. Okay, so let's see. That's good. This is exciting. So kilonewtons per millimeter. Is that going to work? I mean, we know even before we type enter here, right? Kilonewtons per millimeter is going to be the same as dividing this by 1,000,000. Okay, if you do the units out. So let's see. Does it do it? It did. So it's 149, or about 149 kilonewtons per millimeter. Let's go ahead and implement this using Python. It's just the way that we can check our work. So we'll come over here and we'll create a new collab. Here we go. And we'll get to import numpy as MP, control enter, and knows I want to do another line. It's gotten smarter. It's a little bit spooky sometimes to see how good it is. Okay, so we have an E, which is going to be 74 gigapascals. So I'm going to do 74 E9, that will give us pascals. And we have our area, which we're going to say, okay, so that is 1.1 centimeters squared. If I want it in meters squared, I'm going to have to multiply by 10 to the minus 4, because it would be 10 to the minus 2 for centimeters, and now it's squared centimeters, so it's going to be now meters squared, like that. The L1 is equal to, what do we say, 9 centimeters, so that's 9e minus 2 meters, and L2 is equal to 14 e minus 2. millimeters. Okay. And we get the K effective is going to be equal to E times A times 1 over L1 plus 1 over L2, just like that. And we can do a print. K effective is equal to, and we'll do an np.round, and we've got our K effective, and we're going to multiply this, we said, by 1e to the minus 6 because we want it in kilonewtons per millimeter, and we can just do one decimal place, and we'll do kilonewtons per millimeter like that. Let's see what it says. Oops. I guess I went ahead on this, but I think, whoops, now I've got things. It's anticlimactic. Okay, so 149 kilonewtons per millimeter. And if we go back to Google, that's what we got here as well, 149 kilonewtons per millimeter. All right, thank you. I hope you found this example helpful. And I also do believe that thinking about these systems in terms of springs does often make these types of problems where you have indeterminate uh, 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 issues, like we can't just solve this problem with equilibrium, but we had to use constituent relationships to be able to get an answer. So for an indeterminate system, thinking in terms of springs, I think, is quite a useful tool. Thank you.